Hi everyone again, and welcome to the first SIT seminar in the new semester. We are happy to welcome Professor Peltola from Aalto University and University of Bonn. Thank you for accepting our invitation. And before introducing our speaker, I would like to mention briefly our online.
Sorry, Ada, for interrupting. Well, I think the recording is not started. Did you start?
But I heard.
I also heard.
Okay.
I am not sure we started.
Sorry. Okay. Sorry for an interruption. I think it started. I don't know.
It started. Okay.
Sorry for this.
No, it's okay. We started to organize this SIT seminar last year, and we are very grateful to be able to continue this online seminar. And different from the last year, we decided to choose some specific topic for each for talk session. And today's topic is, and also our next three seminars will be about the same topic, which is CFT, conformal field theory. We choose this because it's an important subject for mathematics and physicists, and it's also has an important applications to many areas from string theory to statistical mechanics. And today, Professor Peltola is going to give a talk entitled Towards a Conformal Field Theory for Schramm-Loewner Evolutions. I'm not sure if I can pronounce this correctly, but if you are ready, we can start.
Yes, I'm ready. Thank you very much for the invitation. It sounds like a very nice initiative. First, let me say that I don't see any of your pictures. So if you have any questions, just please shout. I try to keep it, understandable enough, but if you get confused or whatever, just interrupt me. As the topic is CFT, so it's also part of my title. And the second line is Schramm-Loewner evolution, which are some kind of planar random curves that come up in statistical physics. So one of my goals is to try to tell you what they are, so you don't have to know about them yet, and what they have to do with CFT, and maybe a little bit of what kind of features of CFT appear there, but you don't also need to know much about CFT. So should be somehow understandable. I wrote here, so there's some kind of proceedings of the ICMP that I wrote a few years ago about this. So you can go to check it out for more details, because I don't give much details in the talk. And somehow there's much older work in collaboration with many people. So I decided not to list anyone here because I will somehow forget. So let's get started. For kind of the outline of what I want to tell you about is first my motivation to study these things. So actually kind of partially comes from statistical physics in the plane. So some lattice models like the Ising model, for example, especially at their critical points. And in the critical points, we expect conformal invariance in the models when we take a scaling limit. And that's how the conformal field theory should somehow come into play. And we want to understand this mathematically. One way to do that is to look at geometrical properties in these models. I will show you some pictures very soon. So we can look at interfaces between different states of the particles. And these are random curves that we call SLE curves. So the name SLE comes from Schramm-Loewner evolution. So evolution is like a growing curve, and Schramm-Loewner, so these are two names. Loewner was a complex analyst. More than 100 years ago, he wrote some papers about planar domains and how to generate growing planar domains using some evolution. And then Schramm about 20 years ago, 25 years ago, he introduced randomness into this picture. And he was the one who proposed that these curves have something to do with the statistical physics interfaces. So there's kind of a big history underlying here. And basically what you have, you just plug in standard Brownian motion, a one-dimensional Brownian motion, and you get some two-dimensional curve from it. I will tell you how it happens. So this is just the motivation. And what's special here is that how you set this construction will be building in conform invariance that was in this expectation for the models. So this is really kind of a canonical kind of a curve model for geometry of these statistical physics questions. And then going more kind of directly to conformal field theory, to these curves, I will describe you how they kind of interact together. So if you have many of these curves, there's some interaction, and that somehow should have something to do with conformal field theory. We call the interaction how it's encoded into some partition function. Never mind the term so much, it's just some kind of a function depending on endpoints of the curves. And these are supposed to be related to correlation functions in conformal field theory. So this is the last, yeah. Somehow that's what we expect. Somehow the interaction of SLE somehow should translate to correlation functions of fields in conformal field theory. And in the level of functions, you can actually kind of understand this. But the trouble, so I'm proposing some question that I don't know answer to, at least not a complete answer. So if you come from this constructive field theory area, you may have seen mathematicians try to construct path integrals or fields in quantum field theory as some tempered distributions acting on some test functions, or preferably, yeah, operators on some Hilbert space, something like that. So the question I'm posing is, can we somehow realize these objects that you find from the SLE random curves? Can you find some kind of quantum fields in conformal field theory that would be given by these correlation functions that we already understand? So that's maybe for the experts if you already know about this stuff. If not, you can just forget about my question and try to follow the beginning of somehow how the story starts and what we already know. So let's go to some pictures. Here's a provocative statement. So I'm gonna work in the plane. I'm gonna be interested in some lattice models. So here's a lattice, square lattice with two types of colors in it. So that's supposed to be the Ising model with plus and minus spins, which are the two different colors. There's some Gibbs measure, some interaction between them, which is not extremely important here. And what I want to say is that I have there's like a part of Z2, I take some small delta, so some positive delta, I scale my lattice. And if I take delta to 0, the lattice should somehow disappear. And if I do it in such a way that I keep this rectangle fixed, but I kind of just make the mesh finer and finer, it's a bit hard to draw, like that. I'm kind of approximating some continuum thing. So here is a bit bigger, finer mesh picture of a similar type of model. And when the delta goes to 0, then the lattice disappears, and what you expect to end up with is some quantum field theory. And somehow some features of the lattice model should survive in the limit. And if we look at special models, which are called critical, let's just say we focus on them here. Maybe you know them already, maybe not, it doesn't matter. We expect to have a conformally invariant quantum field theory. So somehow conformal field theory in the limit. But then what does it even mean? So if you think about the picture here, so we have these kind of atoms, or I don't know, some particles with some property, like I said, spin up or down, so the color. Of course, I can look at one of them and ask if it's which color it is. But then if I take this limit, I get uncountably many of them. And somehow maybe they're described by some kind of random field, or maybe not. It's very hard to understand. So let's start with some kind of easier macroscopic objects. And one would be look at the interfaces. And I hope in the picture here you see some interfaces. So some curve separating the two colors. And how you can implement that is to put some boundary condition. So here I put so that the blue color is kind of each boundary segment that I'm illustrating has the blue color deterministically. And the other segments have the black color. And inside I sample my model. So then I have some random configuration inside. But no matter what it is, between these boundary points, I always have some interface that's separating the two colors. Of course, there are other kind of loops here as well, but let me ignore them. If I only look at these interfaces, so here's one, then, okay, there is one, but it's ending here. There is one. Not able to follow them completely with this pen. So this is a macroscopic collection of curves. And if I take my delta times delta lattice, these curves will somehow survive and I can study their limit, for example. So that's the approach I'm taking. And let me maybe give a quick example, if you're familiar with the Ising model, for concreteness. So Ising model has these random spins, which are plus or minus 1 or up or down. So each vertex X has a spin. Now the colors is here, purple and black. And probability of a configuration is given by some formula where you have kind of next door interaction between the spins and some parameter. That's the important part, really. That's the temperature of the model for physicists. And if you vary this temperature, you see different behavior in the model. These three pictures here illustrate the variation of the temperature. So here is a very high temperature. You see that the spins are somehow, they look almost independent. So this looks like this television. If you don't have a television channel on, you have this kind of picture, at least in the old times, maybe not with the modern ones. Here is low temperature. So somehow next door spins want to have the same color. And here I put some boundary conditions so that I will have this interface between the corner points. And somewhere in the middle, there's a critical temperature, which where the picture looks like that. And this is the region we are interested in. And here is also an interface between the two corners. It's very hard to find, though. I don't even know if I can. It's very somehow fractal looking, like that. And there are many other models having similar phenomena. It's called the phase transition. And somehow the place where the transition from the qualitative behavior, like from there to there happens, that's called the critical point. And here you can maybe think about this model. If you zoom in or out, it looks kind of scale invariant. So there's some self-similarity in the picture. And that should motivate that actually these models should have conformal invariance if you take this kind of scaling limit. And that's what we want to understand mathematically better. And here's a famous theorem about the Ising model. So if you take these boundary conditions so that, let's see, in the left and top, I have this one color, and on the right and bottom, the other color, and inside I sample my model according to this probability distribution that I wrote down. This interface over here, it's a random interface. It lives in some space of curves, all curves connecting these two boundary points in this rectangle. You can show that it converges. So remember, I was having delta times some z2, subset of delta times z2. I was taking delta to 0. It converges to some object, which is understood. So it's this kind of SLE curve that I want to introduce you to. So this is part of kind of the Fields medal work of Smirnov, but it was actually completed later with many other people. So you can show a statement of this sort. So if you take the Ising model over here, you look at this random interface from corner to corner. You take a limit, you get some known object, which is conformally invariant random curve in the plane that we call SLE. There's some kind of parameter. I write SLE kappa, sorry, SLE3. There's a parameter usually called kappa. Never mind so much. It's just some number that's telling you which model you're looking at somehow. Okay, so in this talk, we would be interested in this, what the limiting these objects are. So I hope it's very visual so far. And also how they are related to CFT. So this is the provocative prediction again. I said any reasonable critical model converges to some conformal field theory. And I could try to start understanding this, for instance, understanding these SLE random curves. And can I say that in the conformal field theory, there would be some boundary fields in these points. So these are the points where the curves are growing from, like that. So can I associate some kind of fields which generate this disorder from, you know, one color to the other color? And there have been some predictions. So in the physics literature, so John Cardy already wrote papers about this from the statistical point of view. He didn't know about SLE curves because that came later, but somehow what the disorder operator should be. Then when the SLE curve was introduced, there was Michel Bauer, Denis Bernard wrote some papers about identifying what kind of field in conformal field theory should correspond to this disorder over here. They've denoted like that. Never mind the notation if you haven't seen it. It's just something that physicists have a guess for what it should be. And somehow why that should be the case, so I will come back to this soon. It's somehow that you can dynamically grow these interfaces using the evolution, and you can try to observe what happens somehow relative to the others. And to this, there are certain kind of natural martingales associated to the evolution. They look like that. So here's a formula, but it will come up later as well. And if you look at the formula, you can compute the stochastic differential of that formula. And if that formula is supposed to be a martingale, in the stochastic differential, there shouldn't be any drift. And if you look what happens then, if you're familiar with stochastic calculus, you will find a partial differential equation for this unknown function that's here in the formula. So this g is some function that we understand. I will tell you about it very soon. This f is an unknown function, and it should satisfy some differential equation, partial differential equation, that is exactly the same that appears in the physics literature for this kind of correlation functions of this particular field that people talk about. So this is no proof or anything, but it's some heuristic that at least somehow this object in the physics book have something to do with solutions of partial differential equations that we also observe from these random SLE curves. And let me go a bit more precisely to these things. So this was just to motivate from the physics literature. So first of all, I need to tell you what these SLE kappa curves are. So you see the pictures, so there are some curves connecting boundary points in the rectangle or in some other domain, but you can understand them more concretely. So here's a theorem by Oded Schramm from 2000s, saying that he was trying to find what kind of curves can describe interfaces in these critical models, such that they would be conformal invariant, meaning that if I map my rectangle over here with the two boundary points to some other simply connected domain, let's say the upper half plane, which is over here, and this point somewhere, maybe this goes to 0 and the other one goes to infinity. It's well outside of the picture. somehow the distribution of this random interface on this side should be just, what is it? It's a probability measure on this kind of curves. It should be pushed to a probability measure on curves on this side in such a way that it's just pushed by the conformal map. So that's what we mean by conform invariance. Kind of, if we understand the model in one geometry, like here, then we can move it elsewhere to any other simply connected domain by conformal maps, and essentially the law stays the same. There's another property that I will not describe. It's kind of Markovian property for the interface. And it turned out that if you impose these two conditions, there's just the one parameter family of possible random curves connecting two boundary points of some simply connected domain. And Schramm called them stochastic Loewner evolution. But then later people started, instead of stochastic, put Schramm here to acknowledge his work. And how does it work? So now if we believe that it's conformal invariant, we can fix our favorite domain, maybe the upper half plane, and look at the curves from 0 to infinity. And then we can move anywhere else by conformal map. And to specify how the curve grows, if I know where the tip at any time t is, I know the whole curve, right? So now let's suppose the curve is simple. So it doesn't touch itself. In that case, like in the picture here, up to this tip, the curve makes some kind of slit in the upper half plane. What I can do, I can just remove that slit and map the rest, which is still a simply connected domain, back to the upper half plane by some conformal map, which I call GT. So it depends on the time. And I can follow where the tip is going to be mapped. It's going to be mapped somewhere in the real line in some position, which is random. And it's given by Brownian motion times some speed. And the speed is given by this parameter kappa. So that's how you see the parameter there. You can do this for any time t. You need to fix a consistent normalization for these conformal maps. But you can do that, for example, saying that they look like the identity map near the infinity, which is the other target point of the curve. And you will have a description, well-defined description of the curve. So this is a conformal bijection. So in particular, if I sample a Brownian motion, I can do backwards for each time t. I know where the Brownian motion is. If I go with the GT inverse, if I know these maps, I will find where the tip of the curve is. If I let the time go, then I can explore somehow the whole curve. So this is often called Loewner evolution. And Schramm is just because he said, okay, let's take Brownian motion to generate a random curve, and let's see what we get. Okay, hope so far so good. Then let me go to this interaction, which is kind of where you really see some conformal field theory coming up. So I was describing one curve with all this picture, but I could have several curves, like in the beginning. So fix several points on the boundary. Say from all of these points, I want to have a growing curve. And maybe, okay, they will hook up somehow in the middle in some random way. Let's not worry about it too much. What will happen then is that if I follow one of them, so I could try to generate it using this Brownian motion recipe. But now it's also has influence of these other points. Because if you think about these simulations this is simulation of the easy model over here. If you have this collection of several curves, they cannot cross each other because they're in the plane and they separate two colors. So there's some kind of non-trivial interaction between them. And if you think about what can happen is that instead of the Brownian motion that was in the previous slide, times the speed, there will be a drift term, which is basically interaction of the other from the other points. So let me show it slightly more concretely. By the way, then here comes a function which is called the partition function. So that's the interaction of the curves. So here is the picture again. I want to grow one curve from some point. So now I took from X. And then there are somewhere other points. I should have maybe drawn them. And some other curves are supposed to be growing from there. If I focus on this one, I can do the same thing. I find the conformal maps. And now I wrote here for you how to find the conformal maps. So there's an equation that is to be solved, which is an ordinary differential equation in time. So for each point Z, maybe Z is there, the image under GT has this kind of time evolution. It just involves the GT and then this W, which was the image of the tip. In our case, it was the Brownian motion or the Brownian motion with the drift. So there are some equations that gives you this evolution. Don't worry too much about them. Okay, so how does the interaction come to play? So now instead of Brownian motion, like I already said, the image of the tip, which is, so the tip is there, the image is here. You take a Brownian motion plus a drift, and you need to figure out what kind of drift there can be so that it's describing this kind of multi-curve model. So there was supposed to be these other curves that I haven't drawn. So you can derive some conditions on what stuff can be here. So basically, your measure will be absolutely continuous with respect to the original one, which only had the Brownian motion. And there's some Radon-Nikodym derivative, which is giving this drift using Girsanov's theorem or Radon-Nikodym theorem, or change of measure, as you will. And somehow you need to impose some kind of properties that classify what kind of Radon-Nikodym derivatives you can have. And the properties come from, basically, if you think about your model, maybe I go slightly back to the picture, this picture for several curves. So somehow there's some kind of symmetry. So here's one curve, here's another one, and so on. And each of them should be kind of just like this original model with just one curve, but in a random domain. So maybe let's take an example. So here is just one curve. And this we understood, this was this SLE kind of curve. So in here, let's say I'm interested in this curve. And I can think about it in such a way that let me first explore this one and somehow erase the part I already know, and that one, and that one. So the other ones, and erase the part that I already kind of know. And if I do that, hope now you can see that the curve we're interested in it's living in a random domain, which is the non-erased part. So it's the one type of SLE curve that we already know, just one curve between this point and this point, but in a random domain. And the random domain is, what's over here. And this is determined by these other curves that I already explored. So somehow the interaction can be used recursively to describe the marginal law of each individual curve like this one. And if you impose this kind of condition, it should hold for any of these curves, some kind of symmetry property. You get some consistency condition for the drift term in this driving function. So now if I go back here, I didn't write it down, but the consistency gives some properties, what can be here. And that's why the formula looks like that. So there's some log derivative of some function. And here are, this is just time evolutions of, this is the tip. And then these V's are just the other points. They may be on the boundary, or actually you can allow them to be a kind of point inside. It goes somewhere else if you want interaction from inside point. But the upshot is that if you add interaction, you will have to add this kind of thing. And I'm interested in a particular type of interaction, which has this symmetry property, so that I can describe many SLE curves. And this interaction will have to do with conformal field theory. Okay.
May I ask something?
Sure.
Sorry, maybe I missed. You already said, I'm not sure. But on the lattice, this kind of curves, physically, it represents what exactly?
In the lattice. So if you look at the picture, there are two colors. And let's say I have this spin easing model, which has spin +1 and -1 in the lattice points. So each rectangle here is a lattice point. It's a bit small, but a small rectangle, the lattice points over here. Each lattice point has a color, random color. So black or purple in this picture. And between the two colors, I can draw this kind of frontier, like also these loops. So there are clusters of black in the picture. These are called interfaces, the loops and curves between the two colors. And this SLE type curve that shows up in the limit is the particular one, which I impose has to connect two boundary points in such a way that I sample my model inside with the boundary condition that all the spins here are plus. So let's say plus is the purple. So here are supposed to be kind of lattice points, plus, plus, plus. And here they are minus, minus, minus. And if you think about it, then from this point and from this point, there must always be, here are minuses and here are minuses, here are pluses and pluses. So somehow you can start looking at this curve whose right side always has the minuses, so that's the black. Left side has the pluses. And for topological reasons, since I'm in the boundary, if I do the exploration, I will end up into this other point. So it's just representing somehow the boundary between pluses and minuses.
Okay.
We can also look at, there was a better, okay, here is the actual lattice. So maybe here is a bit better. Maybe I have, here I can start an interface. Then I follow so that on the left I have this blue and so on. So it goes like that. And it will end there. So here are blacks, right? And here are blues. So I just look at all these different interfaces separating the two colors. And of course, there are many of them. But yeah, if I want to fix some configuration, let's say I fix some points, maybe yeah, here is much more visible. And I impose that from those points, I have this kind of separating interface. Does it make sense?
Yes, yes, yes. Thank you.
Yeah, very good. Yeah, thank you for the question. I guess it's not always so obvious from this what we mean.
Because I thought that someone maybe it shows some defect on the molecule. I don't know. Okay, but it's just...
no, it's a very simple thing.
Okay.
Very simple thing. It's just describing geometry of this. Where did we go? Yeah, of these pictures. And it's easier to fix somehow certain points on the boundary and say that the boundary condition gives you that there are interfaces from those points, so that we have some well-defined kind of curve model that we can try to take limits of. And then in the limit, I have this kind of, yeah, this we already saw. So the limiting curves I can grow using this Loewner evolution. So this is now in the continuum domain. And it's easiest to write in the upper half plane, so that's why I'm writing it like that. But I can go to the rectangle using a conformal map, but these formulas here will look somehow very annoying, so I don't want to do that. Right, so let's see. So I think I was here. Yeah, so I was trying to tell you that if you add this interaction, now it's a bit maybe unclear, it's there. So I have some marked points, maybe this X where the curve is growing from. And then some other points here, Z2, Z3, and so on. So X should be, I guess, Z1. I'm sorry, my slides have mixed notation. Or maybe that should be. Anyway, so the interaction is described by how these other points move under this conformal map GT. And then, yeah, how the tip, where the tip goes. So that's WT. And okay, there's a log derivative just in this variable of the tip of some unknown function that has to satisfy some conditions. So that's telling the interaction. And so if you're familiar with this, maybe you know that if you want to change measure from Brownian motion to something that's absolutely continuous, you can do it using a martingale. So that's the kind of Kirsanov theorem, which is a Radon-Nikodym theorem for kind of probability measures. So there should be some associated martingale, and it turns out the martingales will look like this. So this is a formula that we saw before. So here I have my marked points. I call them X and then some Zs. I think they should be Z1, 2, and so on. So X is kind of where I start exploring, and then the other points are somewhere. And okay, I think I will not go to the details of why the martingale looks like that. But you see that there will be an unknown function of this type and derivatives of the conformal map. So basically what happens is that if you explore up to some time, then how does it look seen from the tip where you already explored? Maybe my curve was gamma, not eta. So the domain has somehow changed, but the model should be the same. So now if I map this one using the conformal map so that the tip goes to this W and those points to go some places, so these points go somewhere, I should be able to somehow, by the conformal invariance that's built in my model, just push everything by the conformal map. And there's some covariance factors, which are these ones. And then these are just images of the points on this side, something like that. But in the end of the day, so if you somehow do computations of this sort, I think I don't have time to really go into it, you will see that this thing should be a martingale. And if this thing should be a martingale, you can calculate the stochastic derivative, like I said already. So there's some kind of chain rule over here. It's a little bit horrible, but when you calculate it, you will get a drift term, which is proportional to this expression over here. So the drift term will always, from Ito's formula, it will have second order derivatives and first order derivatives and some constant terms hitting this function Z. And the G primes, I understand, so they had some formula from before. Maybe I will show it if you're following. Okay, I know time evolution of G. I can also get time evolution of G prime by taking somehow Z derivative of this equation. And it's basically 2 over something. And if you do the computation, you see it somehow over there and also over there. So there's a computation. If you do that, you have these parameters that I haven't told you about, but they come from the model. And this kind of formula hitting this function. And if this was supposed to be a martingale, the drift in the stochastic differential, which was proportional to this thing, that should be 0. So you find a second order differential equation for the unknown function from somehow the consistency of the model that I don't really have time to explain anymore. But the upshot is that you need to find solutions to this equation, and those guys you can plug in here to get your interaction for the curves. And now the point to get to CFT, to conformal field theory, is that this differential equation, so it has second order derivative in the first variable, which is the variable where the curve is growing, and first order derivatives in the other ones, and then some constant term. This is exactly what you see in the CFT book. If you have some, if you look at some conformal field theory book, This is called the null state or null field equation for some particular fields in conformal field theory, which are denoted like that. So in other words, if you're familiar with it, this kind of conformal fields, so this should be some conformal field that is sitting there and generating this curve in some sense. It carries a representation of the Virasoro algebra, which is the conformal symmetry algebra. And this representation is degenerate. So there's some singular vector. And from the singular vector, you have kind of exactly this equation. If you don't know what I just said, just ignore it, because I'm not sure what you guys are familiar with. So the upshot, there's some actually hypoelliptic PD. So there's an elliptic part and some other stuff for the unknown function. So I could just try to solve for all possible functions that, match with my model and try to interpret them using somehow CFT. I think I have a couple of minutes or maybe 4 minutes, 5 minutes. So I can get a little bit to the kind of properties of these and the CFT maybe. There's a lot of information here, but I hope you get the idea. So let's see. I think I already said this. So multiple SLE is just the multi-curve stuff. So here's an upshot. If you want to generate this multi-curve model, this is what I said, is just written differently. You need to find this function that was in the drift. We call it partition function for some reason. And it has to satisfy, this is the same differential equation that I was writing before. I just wrote the delta guy here explicitly. It depends on the parameter kappa. There's always some parameter involved. There's some kind of conformal transformation property, which is over here, which is not super important for us, but just because the model is somehow conformal invariant. So we know how this Z should transform under some Möbius maps. And you can show that solutions to this problem exactly correspond to this multi-curve model. So that's the theorem here is saying that. So that's what I said, that somehow the consistency in the multi-curve model gives you this kind of properties, basically because of the martingale that I was trying to describe. And now we could then, instead of understand the multi-curve model, try to just understand these functions, which are given by some properties. But of course, there are many functions satisfying these properties. So you see that the equation here, the differential equation, for each variable, I have an equation. So there's 2 times n equations if I have 2 times n points, and so capital N curves. So somehow there's always one variable which has the second order derivative, the jth variable, and then the rest are here. So there's a system of equations, but nevertheless, there are many solutions for it. And somehow miraculously, because this looks like an elliptic equation, so if you sum over j over here, then this becomes a Laplacian. And okay, this becomes something not so great, but you can actually classify solutions to this equation. And let me see, I think I'm running slightly out of time. This is the same slide that was before, so we don't really need it, I think. Yeah, so let me show this one. So this is the classification. It looks a bit horrible, but this is repeated, it's the same stuff. So I'm saying here that I can find a basis for solutions to this problem. I call the solution space Sol. It depends on the number of variables. So any number of variables, I can find this kind of solutions. And a nice basis is singled out by properties, how the functions behave when 2 of the variables go together. So it's down here. So maybe j and j plus 1 go together somewhere. You will see that these functions, they will always blow up according to some power law. But if I remove the blow up, I will get something which has same type of function, but here I remove the corresponding j and j plus 1 variables. Or then I might get 0, depending on somehow on my function. So there's some indexing. You see alpha. Alpha is indexing the basis. So there's actually finite basis for solutions. And alpha is kind of representing the following. So it's tiny over here. It's representing which points are connected together by the curves. So in here, these jj plus 1 points, they are connected by a curve. Now the idea is if I shrink these points together, somehow this curve should just disappear. So I'm kind of removing the points over here and just taking the alpha minus that pair. On the other hand, if the points jj plus 1 are actually connected to some other places by the curves, then I should get 0 somehow. I don't allow this kind of limit. And the theorem here, with many, many names, because it's kind of piece by piece built up in the literature, says that I can find this kind of collection of functions that span somehow my set of all partition functions that I'm interested in. This collection we call pure because they kind of generate everything else. They also have something to do with how the curves connect together. I hope it makes some sense. The upshot here is that for these parameter values in a certain range, which is kind of a technical condition, we can classify our SLE partition functions. So we somehow understand them completely. And if I have 1 or 2 minutes, maybe I can mention the question how these are supposed to be related to CFT. So
yes,
if you
go ahead. Yes.
Yeah, so if you're oriented from CFT, maybe you have some further fusion rules. I think I will skip this. This is just some operator product expansion they actually satisfy. But it's a little bit complicated. Let me look for a good slide. Yeah, okay, maybe I go backward here. So this was this conjecture I was saying that this point is supposed to correspond to some disorder operator, and physicists tell me it should have this kind of symbol, and somehow by some martingale heuristics. So now the idea is that if that should be the case, then this partition function z that I was describing in the theorem, they should somehow correspond to correlation functions of this field over here. So now my points are x1 up to x2, and sometimes there is z. So I'm sorry about the notation mismatch, where it shouldn't matter much. So the idea is that in each point, I should put one of these CFT fields if it exists. So here's maybe point x1 and so on. And then the interaction of the curves should be encoded into somehow correlation function of this kind, which is often written like that. But we don't know what this guy is. So it's certainly not a function or anything like that. It doesn't exist as such. But we could ask if it's some kind of random distribution. And maybe I show one last slide about that, just to conclude, if I find it. Okay, maybe here. So now pretend the capital F is this Z and forget about the indexing. So you can, this is a more general setup, but there was some indexing of functions. So let's look at here. So this phi 1, 2. So the prediction is somehow that some CFT field, whatever. So what should it be? What does it mean to be a field? So one way, try to construct them, would be to say that they live in some dual of the Schwarz space. So this is just random distributions. So random objects that you can test against test functions. So they should have some probability measure if they exist and some expected value. And now if you take a kind of moment, so this would be my field tested against test functions F1, Fn in the Schwarz space or some compactly supported or whatever. So maybe, yeah, the value of this phi at x, at some point x doesn't make sense, but maybe the phi tested against some function makes sense. So that's the idea. And if that should be the case, then the moments would be maybe given by some kind of object M, which depends on the test functions, and that's up here. And what is it? You just integrate against the test functions and some kernel, which that should be this Z functions I was telling you about. So my question is, if I take my partition function Z, which have lots of nice properties, if I plug them in to be a kernel of some sort for this kind of moment generating function, can I find a random distribution whose moments are given by this? So that's the question. And okay, maybe I go to the last slide and stop. So the message, sorry, not the last one. This one, yes. So the message is that we have some partial understanding. So once again, this is related to the SLE partition functions, these Zs. So we can show that existence for kappa equals 4, it's a special case. And then if you have existence, you could ask if this distribution is somehow uniquely determined by the moments. And that's something you can also show for some kappas, but I think I shouldn't go too much over time. So I did some work with the master student Simon Schwartz, whose name I put here. So this is not written anywhere else than in his master thesis, and hopefully we'll have some more interesting conclusions later about this. But I think I should stop. Hopefully someone has heard about moment problems, and this is an interesting question. If not, hopefully at least you understood something about interfaces in lattice models. Thanks a lot.
Thank you for this nice talk. Is there any other question?
Yes, I have a question. It is about the fusion rules and more precisely the relationship between the fusion rules and the moment problem. So from what I can tell, I mean, these fusion rules act in a certain sense as kind of coupling rules that you would do in a normal Wick theorem framework for Gaussian fields. But I mean, the combinatorics here looks a little bit more difficult.
Mm-hmm.
So, I mean, if you can say some word about
yes,
these.
So indeed. So this was kind of the basic fusion rule. It depended on the indexing of the basis. Then there's a more horrible one here. So you can have some more general. Somehow the idea picture is here, that the fusion means that you merge some. I think the fusion goes this way, like that. So these are merged, so they become somehow joined. Then the curves go together if possible, and so on. So indeed, in the moment problem, I was actually considering, maybe I should write here, the function, which is the sum of these basis functions. And I could also look at some other combination, which is somehow consistent, because I need to be able to grow the number of points or decrease the number of points in some nice way. So if I fix instead kind of one particular thing, then I have to somehow know how the fusion rules go. So there's a refined question that I didn't even dare to ask, is if you have some individual basis elements indexed by this. So the alpha is kind of a pairing of this sort. Can you find a random distribution for given pairing? So this I don't know. So the theorem actually concerns this case, the moment theorem.
I see. Thank you.
Yeah, I lost it. I think it was here. Yeah, we didn't write it here, but this should be really this kind of, if you think about the curve model, maybe this is motivated. This is sum over all the basis elements. And each basis element was kind of telling you one pairing of the curves. So this is just the average over all possible pairings. And if you think about like the Ising model interfaces, we don't know how they pair up together. So we have to somehow average over everything. So that's why kind of this guy is a meaningful quantity.
Mhm. And I guess that these pairings, in the sense of the picture of the interfaces, are will be non-crossings, non-crossing
Yeah,
pairings.
exactly.
Mhm.
So for example, maybe it's a bit trivial, but if you have two interfaces, so there's kind of this pairing and this one. Yeah, because in the week, I understand. So maybe you also asking if there's this one.
Mhm.
And this is not allowed because it's crossing. Yeah.
Thank you.
So this we called alpha, kind of.
If there is any other question, we can thank again for this interesting talk.
Thank you very much. We'll stop. Also happy to discuss, with anyone later. I know it was lots and lots of information. So I hope you got something out of it.
Yes, I think it's, of course, I couldn't understand all of this, but I can catch some points.
Yeah, very good. It's a very involved area somehow because there are so many objects that play together, but it's quite fun, at least when you can draw pictures.
Thank you so much again. I guess it's dark from your side, and have a good evening, maybe afternoon.
Thank you. Yeah.
And see you in 2 weeks.
Yeah, see you around. Okay, ciao, ciao.
Ciao, ciao.
Thank you. Thank you, Eveliina.
Thank you.
Ciao.
Ciao.